Welcome everybody on board. Adithya and Harendra are going to present on pinpointing memory leaks in production Haskell deployments. And then now, without any further delay, it's over to you, Adithya and Harendra.
Hey guys, thank you for joining in. I'm Adithya. So I work for a company called Composable Technologies. We work primarily with Haskell. Right. Today I'll talk about how to pinpoint memory leaks in production Haskell deployments. And the tool I'm going to talk about is not limited to just pinpointing memory leaks, right? It gives a lot of other information to understand memory of any production deployment, any Haskell production deployment, right? So the primary goal is to answer why the application memory is increasing. Right. So this patch was originally created, or this tool was originally created while we were working with JustPay. Right. So in some of their deployments, we saw that the memory was going up slowly, or even if there was a conventional behavior of memory, we wanted to understand, why that memory exists. What is the breakdown of it? Right. So essentially, there are two scenarios that we are looking at. So we're looking at one, the program is consuming some memory X, and what is the breakdown of X? And two, if the memory is gradually increasing, we'd like to know why. And the most important thing is we want this tool to work in production, right? So for this tool to be useful in production, it should have minimal overhead on performance and a low memory footprint. So why does the application memory increase, right? So multiple reasons. So the actual requirements might require the Haskell memory to increase, or there can be a memory leak, or there can be a fragmentation. I will describe memory leak and fragmentation in the upcoming slides. Right. So memory leak. So before talking about memory leak, little prerequisites about Haskell memory in general, right? In Haskell, the Haskell heap is nothing but a tree of closures, and everything in Haskell is a closure. Your function is a closure. Your data object is a closure. Everything is a closure, right? So everything exists on this heap, and heap is nothing but just a tree of closures. So as Haskell program progresses, right, the closures are formed, closures are alive, and then they die off slowly. The garbage collector periodically goes through the Haskell heap and cleans up all the dead closures, right? It only keeps closures that are alive. So this is the example of a Haskell heap tree would look like this, right? So you have a thread and you have the main function, and you have a list which is basically a linked list of closures, right? So in Haskell, most of the closures are short-lived, right? They die after a few GCs. If a closure is alive after a lot of GCs, right? So if the closure is long-lived, then it either should be part of some persistent configuration, or there should be some reason why it is long-lived, right? If there is no reason, then it's probably a memory leak, right? So this tool is designed to find these kind of leaks. So we can define a memory leak as, some kind of a long-lived closure that we have no reason for its existence. So that's memory leak. Let's quickly look at fragmentation. Some more technical details about the Haskell heap, right? So the Haskell heap is divided into multiple mega blocks, right? Haskell heap is divided into 1 MB mega blocks. And these 1 MB mega blocks are further divided into 4K blocks. So there is something called the mega block allocator that talks to the OS, and it fetches mega blocks in 1 MB or releases mega blocks in 1 MB. And there is something called the block allocator that talks to the mega block allocator to fetch the 4K blocks, or to handle the 4K blocks. So the tree that you saw earlier, the closures are essentially allocated inside these 4K blocks, right? So there are two types of memory in Haskell. There is the pinned memory and there is the unpinned memory. So unpinned memory is the memory that that the garbage collector can move. So pinned memory is something that the garbage collector can't move, right? So here this example is so we can look at this example. So this example has three states of the same memory, right? So three states of the heap snapshot. This is the Haskell heap, state 1, state 2, state 3. In state 1, what you can see is you have these mega blocks, and you have some 4K blocks scattered across these mega blocks. And inside those 4K blocks, you have closures, right? So these are the blue ones are the unpinned closures. The red ones are the pinned closures, right? As time progresses, some of the closures die off, right? So that is indicated by the state number 2. So here you have the light blue closures are dead closures. The dark blue closures are the alive closures. And even in the pinned memory, you have some dead closures and some alive closures. So once the GC, so at one point the RTS has to decide, right? So I want some more free space, so I will do a GC. So once the GC happens, all the unpinned memory is coalesced. It's copied and it's coalesced in one 4K block. But the pinned memory unfortunately can't be moved. So it is not coalesced in any form, right? So because of this one pinned closure, this entire 4K block is held up, and none of the data in this entire 4K block is alive except this guy, and none of this data can be reused, right? And similarly with this guy, because of this one 4K block, this one pinned closure, this entire 4K block is held up, right? And now this entire 4K block can't be used. All of this is dead memory. So this is the pinned 4K fragmentation. So this is what we are calling the pinned 4K fragmentation. So there are multiple levels of fragmentation. There is also the mega block fragmentation that can happen, right? So these 4K blocks are spread across the mega blocks. And there is mega block fragmentation that can also happen, but for now we'll not talk about it. We'll only talk about the pinned 4K fragmentation, which is basically this. Okay, so now that we have defined what memory leak is and what fragmentation is, we have a decent idea about it. We'll have to figure out how to find them and how to tackle them, right? So there are already some pre-existing tools. So the Haskell profiler is one of it. So you can compile your Haskell program with the prof flag enabled, and this will give you access to the standard profiling mode, right? And the standard profiling mode is very powerful. It's very matured. There's also the eras profiling in the profiling mode that can help you distinguish closures depending on the age, right? And with respect to fragmentation, though, there is limited amount of information available with the current profiling mode. But because the profiling mode does so much, right, it has to keep track of a lot of things, right? It makes the program inefficient, right? Profiling mode is inefficient by default because first off, it does not let optimization to happen properly, right? But to tackle that, the fprof late flag was introduced. So this basically adds the cost centers after optimization. But even if you take optimization out of the picture, the fundamental problem of profiling is that because it has to track some information, it has to track all of this information. Allocation of a closure comes with a lot of baggage, right? So it's costly to allocate closures. Right, so we will just look at some technical details about what happens during profiling, right? So every closure follows the same format, right? It has a header and it has some payload. So that's how every closure in Haskell looks like. In the header of every closure, we have the info table, which we can ignore now. The important thing is when the profiling mode is enabled, we have yet another header called the STG. So STG prof header, which has all the profiling information. And in the STG prof header, we have the cost center stack. And along with that, we have some other things. But maintaining this cost center stack is costly, right? So to maintain this cost center stack, many instructions are added. While we allocate closure, many instructions are added. This makes allocation of a closure costly. And if there is a lot of overhead for closure allocation, then your entire program becomes highly inefficient, because in production you have like thousands or millions of closures. So how do we solve this problem, right? So what does this new tool do, right? So we take the standard profiling mode and we churn it down. We remove all the unnecessary, or we remove a lot of information that the default profiling mode keeps track of, right? So we eliminate cost center stack and friends, right? And we minimize the number of instructions that are introduced, because we want to keep track of certain things. So we keep track of only one thing, which is the GCID. So for every closure, we attach a GCID. We'll talk about GCID a little more later. So if we look at the CMM code generated for all the three different modes, right? So CMM code generated without profiling, CMM code generated with the lightweight profiling that we have, that this talk is about, and the standard profiling. You can see that there are the only thing that is added in this lightweight profiling is storing of the GCID. The CCCS actually has the GCID. So it stores the GCID and it takes care of one more flip bit, but this we can ignore. We don't need to really understand the program here. You just need to understand the diff, right? So in this case, without profiling, if this is how it looks with lightweight profiling, we add 2 more lines to it, right? And with standard profiling, there is 1 more line here, which basically keeps track of, which basically maintains the cost centers. I mean, this is not the only line added. If you look at the entire program, then across the program, there are a lot of places where you keep track of the cost centers, but the slide was not enough for all of them. So I just put, the minimal required to show you the difference. So we will look at the new profiling tool in action now. We will see how we can use it for debugging things in debugging the problems that we have, right? So first thing is we have to make sure that we have to see that memory is increasing. So you look at the output of top and you see, okay, the memory is increasing, and any steady memory increment should be investigated, right? So there are 2 potential reasons of unreasonable memory increase, which is one, the pinned 4K fragmentation that we talked about, or the live bytes are going up, right? So we need to first figure out what the problem is. So the assumption is that we first have built our executable with the new profiling mode enabled, right? When the new profiling mode is enabled, we get some premops that help us control a few things, right? So for example, the lightweight profiler has a premop that can start recording memory statistics periodically, right? It can record them periodically or on command, right? And these specific statistics represent the snapshot of memory at one specific time, right? So the snapshot of a heap, basically. We'll look at how these statistics look like and what we can glean from them, right? All of these statistics are basically dumped in the heap file. So there is a .hp file, right? So all of these statistics are currently dumped in that HP file when the profiling, when the primop says, trigger the profiling. When the primop says dump the statistics, they're dumped into a file. So we look at the file now. Okay, so the first thing we see is that it reports GCID. So GCID starts from 0 and it increments at every GC, right? So GCID 34 means that 34 GCs have happened when this snapshot was, when these statistics were, being reported, right? Then we have the summary of process memory, right? This is what the output of top will look like, right? This is what top will report to you. So these statistics right now are sourced from /proc, right? So the process memory statistics are currently only available on Linux, but it's not a big deal to figure out these statistics on other platforms as well, right? So the process memory, the total RSS, total resident memory, will include everything, right? It'll include your program text, your shared libraries, your mmap memory, foreign allocations, and the Haskell heap. And the RSS, the resident memory, is further divided into two parts. So you have the file maps. There's not a lot you can do about the file maps, so we'll ignore that. And the anonymous memory. The anonymous memory is interesting, right? The anonymous memory has, so it basically has everything other than the file maps, right? So it has the C heap, it has the program, it has any foreign allocations, and the Haskell heap, which is the most interesting part. And in any Haskell application, though, most of this anonymous memory is basically Haskell heap, right? So now let's just dig into the Haskell part of the program. There is this mblock allocator summary. The mblock allocator summary gives you the totality of Haskell heap. So this is the entirety of Haskell heap. It basically says that there are 6 mega blocks allocated for the Haskell heap. So one small thing that you can say here is that, okay, the mega block allocator says there is 6 MB, but the process memory says that the anonymous memory is only 5 MB. This is because a lot of memory might not have been paged yet, right? So a lot of pages might not have been accessed, so they have not been paged yet. But this is the totality of Haskell heap. So memory mblock allocator has requested 6 MB from the OS, and it's getting that 6 MB. So 6 MB, so 6 1 MB blocks are further divided, like we've talked about previously, into 4K blocks, right? So 6 mega blocks will approximately have 1512 4K blocks, right? And out of these 1512 4K blocks, the block allocator has taken away 1358 4K blocks, and there are 154 free 4K blocks. So now let's look at the 4K blocks. So 4K blocks are quite interesting, right? It's more interesting than the mega blocks because it'll give us a much more deeper view of the Haskell memory. So we have the block allocator summary first. It basically says that out of the 1358 4K blocks, 36 of them are used and 1322 blocks are free, right? Sorry. And out of the 36 used 4K blocks, 7 of those 4K blocks have unpinned memory, right? And 28 of those 4K blocks have pinned memory. That's what this breakdown says. Here I've highlighted the pinned part because pinned part is the most interesting statistic to look at when we are talking about about the 4K fragmentation that we have talked about, right? So out of this 28 pinned 28 4K blocks that have pinned memory. 26 of those blocks have large allocations, and 2 of those blocks have small pinned memory allocations, right? And the small pinned memory allocations is the culprit for 4K block fragmentation. Because large allocations basically use up the entire block, right? So you either use up the entire block or you free the entire block. But in small pinned memory allocations, you might not use up the entire block, right? There might be data that is dead in the block, but you are still not giving away the block because you are pinned. So that's the block allocator summary. Now let's look at the block level used. So there are 2 ways of accounting for memory in Haskell, right? So the first way is we look at the mega block itself, the mega blocks themselves, and we look at the 4K blocks, and we look at the block descriptors, right? What the block descriptors tell us, how much of this 4K block is used, etc., etc. That's one way. And the other way is we traverse the Haskell heap. We traverse the Haskell object tree. That is the second way of accounting for memory that is used, right? So in here, we are using the first way. So in this specific code block uses the first way, which is we look at the mega blocks and we look at the 4K blocks, and we look at the block descriptors, and from that we calculate the amount of memory used, right? So here you can see that out of 147 KB available, 118 KB is used. So rest of the memory is basically slop. I mean, in this case, rest of the memory, it could include a memory that is yet to be used also, but that is very insignificant, right? Because it's 147 KB. At max, that is 2 blocks, right? 8 KB. So basically 20% of this, most of the 20% of this is basically slop. Slop is unused memory. What I mean by an unused memory is, let's assume you have a 4K block, right? And you have 3 allocations of 1K each. And then you have a 4th allocation that requires 1.5K. And you cannot use that block anymore, right? Because there's no space in that block. So you have to use a new 4K block. Because of that, there is 1K in the previous 4K block that is left empty, right? That is unused, and it can never be used again. I mean, it can never be used for the time being. So that is basically slop, right? So that's the unused part of the 4K. So let's look at the pinned part, the interesting part. Here it says that the 4K blocks that have large allocations have 87% utilization. So 13% is basically slop. And the small for the small allocations, for the small pinned, the blocks that have the small pinned allocations, 2600 bytes are used. Only 63% is used, right? So 40% is basically slop. And you have the current pinned block also. So in this case, 56% is used, but the rest of the 44% might not be slop only. It can be unused memory as well, right? So we look at the small memory here. The blocks that have small pinned allocations here. So it says that out of the 4K, 2600 memory is used. Rest of the thing is slop. We will look at, the point is, out of this 2600, if all of the 2600 bytes here are live, that means there is no fragmentation. If any of the, out of the 2600, if there is out of the 2600, there could be dead memory as well. I mean, that we'll have to figure out later, right? We will be doing that now. So like I said earlier, there are 2 ways of accounting for memory. So there is the block level accounting, where you look at the block descriptors. And there is the heap level memory, the heap level accounting, where you go through the object tree and, count the live bytes. So that is basically just another view of the block level memory, but it gives us some more interesting information, right? So this is just the previous thing copied. So this is the result that we have when we traverse the heap itself to figure out, we traverse the object tree of the heap to account for the memory, right? So here, the most important. So what this says is, out of the accounted memory, that total used bytes. So out of the total used bytes here, so these are the total used bytes, the 4912, 98272. These are the total used bytes. So what this basically says is, out of these total used bytes in this block, how many bytes are live, right? So in almost all these cases, except the blocks with small pinned allocations, all of them should exactly match. So all of them should always have 100%. So large pinned allocations, the blocks with large pinned allocations should always have these live bytes, right? Whatever space is used in that block should always be live. If it's not live, that block should not be there, right? But that is not the case for small pinned allocations. For small pinned allocations, this metric here tells us, if there is fragmentation or not. So in this case, for this whatever example that has been used to get these statistics, all of the 4920 bytes that is used is live. So there is no pinned memory fragmentation here. If this number is not 100%, then that means that there is pinned memory fragmentation. If the number is 80%, then there is 20% pinned memory fragmentation. 20% of these bytes are dead, yet they exist. We are just keeping them. Right. So at this point, after looking at some rolling stats, there are two things that we will know, right? We will know so we have all the stats in the world, right? We have all the stats and we have some rolling stats because we can periodically print them. We will know if the live memory is increasing or if the fragmentation is increasing, right? If the 4K fragmentation is increasing. If the fragmentation is increasing, then we should look at where the pinned memory is being allocated, right? Where and why is it being held? What holds it? So for that, we have to look at the heap, which we will look at in some time, right? But with respect to few words with respect to pinned memory is that you should only use pinned memory while interfacing with the OS, unless absolutely required. Right? In most cases, it's better to use unpinned memory because because the fragmentation does not occur because of unpinned memory. Right. So if live memory is increasing, we should start looking at the heap. Right. We should start looking at the heap more. We should inspect the heap more properly. Right. So how we look at the heap generally depends on the context of our problem. Right. So the current tool that we have has premops that can dump the heap based on certain that can dump the heap and dump a filtered version of the heap. I mean, I will talk a little more about it in the upcoming slides. But basically, the most convenient thing to do is dump the entire heap, right? But dumping the entire heap is not viable in production. So we have to be a little more clever with respect to what in the heap that we want to dump. So heap, again, just to refresh, heap is again just a tree of closures, right? It's just a object tree of closures. And right now with this tool, we have attached a GC ID to each closure, right? So if we look at the Haskell heap, which is just a tree of closures, if we look at a specific closure, we have the information of when this closure was allocated, how many GCs has it survived, right? And etc. And this information can be used quite a bit for figuring out if this is a leak or not, right? So first we'll look at the heap. First we'll look at the dump that this tool provides us, the heap dump. We will use this sample program, right? So because I want you guys to make some kind of a correspondence to the heap. I want this sample program to correspond to the heap that we look at. right? So this is just a sample program. All it does is there is some global IORF, and there is some loop that bumps a counter in that ref. So this is the primop I was talking about. So this basically says dump the entire heap, right? Also, we have intentionally introduced a memory leak here, right? So modify IORF will cause a memory leak. This is not a strict function. This is a lazy function. So these +1 thunks will get accumulated and they will become huge. And we are looping this 100,000 times, right? So now we look at the heap dump that we get after compiling and running this. Okay, so the heap dump will look something like this. It actually has a lot more information than this, right? But it will not fit in the slide, so I have removed as much as possible, right? It has the exact source locations, which files, which line numbers, etc., right? And this is very accurate memory accounting, right? So if you the numbers that you see here uh, exactly correspond to the numbers that we get in the rolling stats. I mean, in the stats that we have seen earlier. Um, so the heap here starts at the bottom. So here we have the root of the heap, and the tree grows upwards. So that's how this file looks, right? So this is the root, and these are the children. So the children are indented. You also have a level for children if indentation is not possible. This basically tells the indentation level. So the most interesting number here that we can look at is the GCID, because all these, so each line is basically a closure, right? This is just a tree of closures. Each line corresponds to one specific closure. And the most important number we can look at is the GCID. And so the number before the colon that you see here is the GCID. The GCID 0 here means that this guy has been allocated before anything, right, at the start of the world. And these things will exist till the end of the world because these are required for the entire program to run properly. Right, so you have the entire closure. So you have a tree of closures. So if you look at this tree properly, if you look at this tree properly and you have the context that, okay, there is also a leak, you can see that there are closures with GCID 50, GCID 60, and so on. Like there are 99,000 closures. So this is basically, I mean, I've removed all of it. It's basically condensed tree, right? So there are 99,000 closures in this heap that have been allocated over the course of this 99 GCs, right? With numbers 50, numbers 60, and so on until the GCID 99. And this is peculiar, right? Because if you have, so this is basically a long living closure. So this guy has been allocated right after, the 50th GC, and it exists till now. And now is basically 99th GC. So it exists after 50 GCs, which should not happen, right? And I have no reason for this to happen. Because I know the problem, because I know the context of the problem, there's no reason for this to happen, right? And rightfully so. This should not happen because this is a leak, right? And you have some information attached to this leak, like the modify IORF that comes from data.iorf. So you have some hints attached to this closure that has been very long living, right? And your job now is to go back to the code and figure out, okay, this guy has the leak. So where is this guy? And you can fix the leak. So like as we have talked earlier, this tree also has one more indicator here, which is not shown, but basically every closure is either a part of large, small, or pinned 4K block. So in this tree of closures, you can also find out the closures that are small, that are inside the small pinned 4K blocks, right? So that way you can also see why those closures are being held on. Why is it small pinned, right? If that's even required. So this is basically the entire heap that you can dump, right? But in general, dumping the entire heap again is not viable because one, it's very huge, and there's a very huge overhead for dumping the heap in production. And two, is just a lot of data, and you don't want to look at a lot of data, right? So what you want to do is filter this data out. So depending on the context, depending on the problem that we are facing, we can, and depending on the stats that we are looking at, we can filter this data out. Right. So so a lot of filters available. Like we can do a rolling window. For example, assume that now let's say the GCID is 99, right? If I were more clever while dumping this heap, I would probably say, okay, given that I know the problem, I only want to dump the heap with the closures that have been allocated between the GCID 50 and 60. So essentially, whatever the current GCID is, I want to dump the closures that have been allocated between the window of current minus 50 and current minus 60. Between that window, whatever closures have been allocated, I want to dump.
Just a friendly reminder, 5 minutes to go.
Yeah, sorry. Yeah, so there are many other filters like that. So essentially your task now is to, figure out what filter works best to describe the problem in more detail and to filter out the unnecessary information, right? And you can dump the heap periodically, or you can dump the heap once in a while programmatically. So let's say if you see a huge memory spike and you want to figure out what's going on, right? You can programmatically dump the heap, and it'll dump the heap after the next GC. And then you can, study the heap. So the GHC patch is, I will attach the slides later in the talk itself. I mean, on the website. So you can look at the patch itself and you can play with it. You can, there's still a lot of things we need to do with the patch. So you can play with it and try to debug some of the memory issues that you have. So again, most of this work was done while we were working with JustPay, right? So they had some issues with their deployments, and that's where the idea of this tool was born, right? So, and most of this work was done by Harendra, right? My co-speaker who is not speaking now, right? So a lot of time has been put into this. So in the near future, we would like to get this, the lightweight profiling, we would like to clean it up and get it merged to GHC, right? So right now we only report the 4K block fragmentation. So we would also want to report the mega block fragmentation because that will also be very useful, right? And we want these dumps to be automatic. So somehow we have to monitor without having a lot of overhead. Somehow we want to monitor this live data fragmentation and auto dump these statistics based on some heuristic filters, right? To make it easy for the programmers. That's my talk. That's all I have to say, and I've lost my voice as well, saying a lot of things. I will take any questions now.
Thank you. Thanks, Aditya. Thanks a lot for the wonderful talk. I hope everybody got a lot of info out of this. There was one question which is already answered. I think Harendra answered that for Aaron. Anybody has any other questions, please feel free to share here. Or after 2 minutes.
There is one more question. How big is the GHC patch? It's quite big as such, but it's not very invasive. There are invasive changes are in the profiling code, like the instructions where the profiling instrumentation happens. So there are some quite intricate changes there, but otherwise the patch is pretty clean. So a lot of work had already been done in the Eraj profiling by the GHC folks, but we made this patch for 8.10.7 before, where those changes were not there. But now we merged it with 9.2, where those changes are there, so we could use those changes now. So it's come off pretty well.
Thank you. Thanks, Harendra. We have something in the chat. Okay, no, that's it. Okay, I think so. It's about time. So once again, thanks, Harendra. Thanks, Aditya. I'm just closing the session. All of you are please welcome to join Hangouts.